Alright, today's lesson is going to be on evaluating and graphing logarithmic functions. A logarithmic function is the inverse of an exponential function. So what you're going to see in class is a need to find an inverse of an exponential function and algebraically not knowing how to find it. And that's where logarithms come into play. Now the definition of a logarithm is simply this: the log base b of y is equal to x, if and only if b to the x equals y. We read the log as log base b of y. If b is 10, we normally don't write that. You won't see log base 10, much like when we do square roots. We don't see the 2 for the index. So just be aware of that. Logarithms are inverses of exponential functions, and exponential functions are inverses of logarithms. So we're going to spend some time with logarithms today. Now, the first example that we're going to look at is rewriting logarithms, kind of using that general definition of what a logarithm is. Okay, so you can see that we have three examples here, and we're going to write each of these logarithms as exponentials. Now, you can go either way. You can start, for example, here if you have an exponential and write it in logarithmic form. So these are interchangeable. So the first one we have is log base 2 of 8 is equal to 3. Okay, what I like to think of as whatever the log is equal to, that's your power. So if we look at it, the base here is the base for the exponent. The log is equal to 3, that's our power, and 8 is what we should have the log equal to. So log base 2 of 8 equals 3. So this answer should make sense. It should be a true statement if you've changed correctly, if you've gone from logarithmic to exponential form. You should have a true statement here. Okay, so 2 cubed is 8, so that does work. Now, second one is log base 4 of 1 is equal to 0. So we're going to rewrite that. This number b, or this letter b, is always going to be the base of your exponential function. So our base here should be 4. Our power is what the logarithm is equal to, so 4 to the 0 power is equal to 1, and anything to the 0 power is 1. So that also makes sense. Lastly, we have log base 1/4 of 4 is equal to -1. So our base is -4. Our power is -1, and our should be equal to 4, and 4 to the negative first power is 4. So that's how we rewrite logarithms. And please remember, you can start with the logarithm and write it in exponential form, or you can be given the exponential and write it in logarithm form. These are inverses of one another. So the second example we're going to look at is actually evaluating logarithms. We can find answers. We can find that missing x, or what that logarithm is equal to, like we did in the last example. So basically what we're looking at in this first example, we're going to evaluate log base 4 of 64. So basically we're missing the equals part. Okay, that's what we're going to find. So you got to think to yourself, 4 to what power is 64? That's the idea. So when you think about it, 4 to what power is 64? Well, 4 cubed is 64. So x in this case is equal to the power. It's 3. X is 3. B, we're looking at log base 1/5 to the 125. Okay, so 1/5 to what power is 125? Okay, 1/5 to the -3 power is 125. And if you think about it, 5 cubed is 125. So 5 to the -3rd is 1/25. So this makes sense. 1/5 to the -3rd power is 125, because to get rid of that negative exponent, we would flip the fraction to 1/5. The second part of this is graphing logarithms. Graphing logarithms can be tricky, but we're going to actually use the definition of what the inverse is. So for example here, we're going to see log base 2 of x. We're going to graph that. Well, in order to do that, we're going to follow some simple steps. Number 1, you plot the inverse function, the exponential. Okay, the parent function. Number 2, just switch x and y and that's going to give you your inverse function, the logarithm. Okay? And number 3, you'll see later on, we're going to apply a transformation. So when you're talking about graphing logarithms, it's very important that if a logarithm is the logarithm's an inverse of exponentials, that means the domain and range switch. Because when we talk about inverse functions, one of the first ways we could find inverses is switching x and y. So that means your domain and range change. Your domain goes from all real numbers to x is greater than 0, and now your range is going to be all real numbers. So let's look at the graph. Log base 2 of x, that's the inverse of y equals 2 to the x. So in blue, we've plotted y equals 2 to the x. We've plotted 0, 1, 1, 2, 2, 4. To get the inverse, you switch the order. 1, 0 becomes, 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. And now here in the black is the y equals log base 2 of x. Notice how the asymptote is vertical now, not horizontal. So x has to be greater than 0. We're not crossing the y-axis here. And the range is all real numbers. On this next example, we are actually going to plot log base 3 of x again. So it's a similar function. We're going to state the domain and range. So number 1, determine the inverse. The inverse of log base 3 of x is 3 to the x. Number 2, we plot the inverse. We did here. We plugged in 0, we get 1. We plugged in 1, we got 3. Step 3, you plot y-x. Well, that means interchange the ordered pairs. 1, 0, 0, 1 becomes 1, 0. 1, 3 becomes 3, 1. There's our graph. Log base 3 of x. Domain is 0 to infinity. Range is all real numbers, negative infinity to infinity, and you should see that from the graph. Remember, inverses are just reflections over the y equals x line. So if you drew that y equals x line, you could reflect over. So just remember that. And our last example, we're applying a transformation. What's key here is that your h value is actually going to be your asymptote, not the k. So the x, if x was 2, we'd have 0. So that's actually going to be our vertical asymptote. We'd have a vertical line going through 2. We see 3 graphs here. So let's look and see how we plot this. Number 1, we plot the parent function, y equals 2 to the x, because it's base 2. We're ignoring the transformation. So you plot y equals 2 to the x. Secondly, we plot y comma x. That would give us this function, and that's what you see in black. So 2 to the x, we had 0, 1, 1, 2, 2, 4. We interchanged all those points. 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2. And there's our parent log function. So finally, we have to apply the transformation. All these points in black have to be moved 2 right and 1 down. So you move each point 1, 2 right, 1 down. 1, 2 right, 1 down. 2 right, 1 down. And we plot our function. So this third graph is the final graph here in blue after we applied the transformation. So there are 4 steps to think about. Still plot that exponential function. Switch your points, and that would give you your parent log function. Then apply the transformation. In this case, 2 right, 1 down. Okay, h is always going to be the vertical asymptote with logarithms. Okay, so our vertical line is x equals 2. So notice how our domain is 2 to infinity. Okay, and our range is still all real numbers. The range is not going to be affected with logarithms. Okay, the range is always going to be all real numbers for logarithmic function. The domain changes as your h value changes. So this is logarithmic functions. I hope this really helped out. If you have any questions, you guys go ahead and email me, and we'll see you next time. Thanks.